Okay, physics 30, so I'm going to go over assignment number 2 here for magnetic fields. I'm going to do slightly different than I usually do. I'm going to actually use a physical piece of paper here, and I'm going to show what I'm doing with my hand to determine the direction using this piece of paper. All right, so we've got a little bit confusing trying to figure out, okay, what's this mean when it's coming towards my face? That means it's actually going into the page. So I'm going to actually put my picture up here, and then put my thumb into the page or whichever direction the current is going. All right. So question number 1 here has to determine the magnetic field around these current carrying wires, and it's showing the electron flow in each. So the first one has an X going into the page, and then you can see in the second one here, the current is flowing from left to right. Okay. So they're talking about electron flow here for both of these. So I'm going to be using my left hand. Okay. So let's see what happens here. So that's not what I wanted to do. I want to make this bigger. Okay. So here's my page. Okay. Exposure is just a little bit much there. I can focus on my page or not. Okay, this is my page. So what I'm going to do with my page, because there's an X there, I'll move my cursor out of the way. I'm going to put my thumb into the page. I use my left hand here. My thumb into the page, and my fingers are going to curl around the current carrying wire in the direction the magnetic field is going. You can kind of see here in this picture, the way I have it, it's going in this nice little, is that counterclockwise direction? Okay. And then if I did for this one on the bottom, I'm going to put my thumb in the direction of the current carrying wire. So my thumb's going to go in this direction. My hand's going to wrap around this way. So it's going to go up the front and then down the back. You can see that's what's happening with my hand here. It's going up the front and then down the back. So what's that look like when I draw it out? Well, exactly what I said here. So I put my thumb into the page like I did. It's going counterclockwise. So I'm going to draw a circle in a counterclockwise direction. So that's my magnetic field. And then I'm going to draw a concentric circle. Another circle above that one. And then another one out here. I'm not going to draw them all because it's just going to get in the way of the next one down here. And this one here, like I said, it went up the front and then down the back. It's kind of hard to draw that three-dimensionally like this. If you could see that there's a slight little shape to here, you could see that's what's going to happen. And then there's going to be a circle around that one, a bigger circle. So this first diagram is now just a cross-section of what you see down here. Okay? Yeah, looking pretty good. If you don't want to draw the three-dimensional things, you could say it's going up the front, then into the page on the top. So I put a bunch of X's here. That's my magnetic field, and then it's going to come out of the page on the bottom. And then if it comes out of the page on the bottom, it's going to go up the front to the top there. Okay? So that's what it looks like for those two. Sorry, kind of in a weird spot with my camera. Okay. For the next one here, we've got a free moving proton. So because of the proton, I'm going to be using my right hand this time. Okay. So I'm going to pull out my sheet to try to determine which direction. So state the direction of the initial magnetic force on the proton and the type of motion. When I'm talking about type of motion, I'm talking about, is it accelerated motion? Is it circular motion? Is it parabolic motion? What kind of motion does it look? We'll get to that part in a bit. So let's look at this picture. Okay. So I'm going to use my right hand. Okay. Yeah. So I'm going to use my right hand here. With my thumb in the direction of the proton, and then my fingers are going to have to go into the page. It's going to be a bit trickier for me to do this. All right. So my fingers are going into the page. My thumb is the direction of the proton. Then you notice my palm is facing upwards here. So using my right hand this time, thumb in the direction of the proton, fingers into the page. You notice that my thumb is going upwards. Or my palm, sorry, is going upwards. So my initial force here is upwards. So what's the direction of the initial force? The initial magnetic force is upwards. Oops. Yeah, okay. Yeah, okay. The initial magnetic force is upwards. And the type of motion I'm looking for here, type of motion, is circular motion. So remember that circular motion. If the force is always perpendicular to the motion of the proton or the motion of the particle, then the direction, so the type of motion is always going to be circular. So what I mean by that is that, what I mean by that always perpendicular part is that this force right now is 90 degrees. So that force is 90 degrees to this. Now, when it changes direction, because that's what that force is doing, is acting 90 degrees, so it's going to change direction. So it's going to slightly move off and maybe move this direction now. So that's going to be the direction of the proton. But because of the direction of the proton is that direction, I put my thumb in that direction now. It's going to be tricky to do. Got to use my right hand, sorry. Thumb in that direction. And then my force is now going off at an angle going this way. Okay? You notice that's still 90 degrees. Okay? That force is going to be 90 degrees. It's going to change its direction again. Now it's going to be going upwards. And its force is going to change direction. And because of that, the motion of this is going to be circular. It's going to be circular motion, not going to be parabolic motion. In parabolic motion, the force is always going one way. It's always going down or going sideways. It doesn't change direction based on the motion of the object. So when I throw an object, like this juggling ball here, and I throw it across the screen, the force of gravity is always going down. So it's going to have a parabolic motion there. If the force of gravity were to change direction as it moved around, it would orbit. It would go into circular motion. So this is the circular motion since. I'm just going to put a little since here. Since the force always acts towards a center point. So it's central seeking. That's what centripetal stands for, centripetal. Now, the key to this is that it doesn't change speed. It changes velocity all the time because its direction is always changing, but its speed remains the same because its force is constant. It's a constant force inwards. That force is not changing. So its speed wouldn't change. Current carrying wire is shown in an external magnetic field. They show me that's electron flow here, magnetic field. What's the direction of the magnetic force? If it's from, they just tell me the current flows from left to right. Okay, so you pull out your picture again. Okay, pull your picture. I'm going to use my left hand. My thumb is going to go in the direction of the current. My finger's in the direction of the magnetic field. And you can see that my palm here is going into the page when I did that. So my force is into the page. I'm sorry about my handwriting today. There you go, into the page. The two sources of the magnetic fields required to produce a motor effect on a moving charge. A motor effect is this force, right? The force that we're talking about, using my third hand rule. Now, the two forces, you even talk about this in your third hand rule, the fingers are an external magnetic field, and the other magnetic field is caused by the moving charge. So the two sources is one is from the moving charge. Oersted said that a moving charge will produce a magnetic field. As long as it's moving. If it's not moving, it just produces an electric field. A moving charge produces an electric field as well, but a magnetic field is, and anything with mass has gravity. So that's just all the fields that these produce. Okay. Now the other one is from an external magnet. This could be a permanent magnet or an electromagnet. Oh, I could be missing the A on electromagnet. Okay. So I gave you permanent or electromagnet. Those are my two fields. All right. The moving charge or some external magnet. There were two fields cause of force. Here an airplane is flying east. Never eat, ready, wheat. So my airplane is flying east at this point. So he's flying this direction, so I can just draw an airplane. Okay, so there's a top-down picture of an airplane. There's this window, we got some jets in here too. Okay, now this top-down picture of an airplane is moving east. You can see in this picture here. As a result of its motion, one of the wings is detected to have more electrons than the other. So let's see, it's flying over the Earth's magnetic North Pole. So remember that the Earth's magnetic North Pole is technically at the South Pole down here. The field lines are going to be coming out of that side. They're going to wrap around and then into the top. I'm just worried about here. So the airplane's down here, is flying over the North Pole. So that means the magnetic field is coming out of the ground at this point. Okay, and he is flying this direction. Okay, so using our hand rule. So here's my piece of paper. My finger is going to be coming out of the page, and my plane is traveling this direction. Okay, so it's traveling east. My finger's coming out of the page. My palm is upwards. So my palm is forced upwards. So that means all the electrons, I was using my left hand there. Okay. Yeah. So I was using my left hand. So all the electrons in this airplane, because they were moving with the airplane originally, that's why my thumb is going in that direction. Okay. My thumb is going in that direction. The palm's coming out of the page. So let's take this out again. So out of the page, that direction, palm is upwards. So all these electrons are going to be forced upwards to this top wing. All right, so this wing here. So from the perspective of the pilot, that is the left wing. Okay, that's a weird sentence. The left wing will have the electrons. Why does this occur? Because those electrons, since the moving electrons produce a magnetic field. Okay. So those electrons are moving, they produce a magnetic field, they interact with the Earth's magnetic field, and they get forced in a certain direction. In this case, the force is upwards, so that's my magnetic force there. Okay. What is the principle of Lenz's law? The principle of Lenz's law is this idea that you just can't get energy from nothing. So the Lenz's law, just by definition, is the induced current caused by a changing magnetic field is in a direction to produce a magnetic field that will oppose the changing magnetic field. You could think of this like Le Chatelier's principle in chemistry, where something happens and then the reaction will react in a way to kind of change it back to what it was before. You think of this as Newton's first law, where it just doesn't want to move. You apply a force on it, it applies a force back on you. There's a lot of different ways to explain it. You can just look up online here. Wikipedia has a pretty good definition of it. Just talks about how the direction of the current induced will be in such a way that it opposes the initial changing magnetic field. So it's just trying to stop it from moving. Okay. Now, Lenz's law helps us explain what happens in number 7 here. There's lots of ways you can explain. You can talk about, if you look up this kind of example on Google, or just search on the internet here. They talk about diamagnetic materials and talk about that. The main key part of this, diamagnetic materials they're too weak for this one. The key part of this is it's about Lenz's law. So inside a grape, so imagine you have a grape on this straw, and just imagine there's a counterweight on the other side, and you bring a magnet close to this grape, okay? And if you bring a magnet close and you move it towards it, the magnetic field will be changing. Because it's a changing magnetic field, it's going to induce a current in my grape. And they use a grape here because the grapes are very acidic. They have ions in them. So the ions inside the grape, so whatever these positive ions are, they're not protons, they're ions, so they're in solution, are going to move in such a way, counterclockwise, clockwise, to produce a magnetic field to oppose this one. So if I said there was a north coming this way, a north would be produced in the grape on the closer side to try to push that magnet back. Right, and there'll be a south on that side. If you want, you can use your hand rule, because this is positive stuff. I can use my hand rule to try to determine the direction of the ion flow here. They'll probably start flowing in that direction to try to oppose the motion of the magnet. It's really just easier just to say it, right, rather than to actually explain what happens there. But you can think about this is my explanation. This is a very simplified explanation. There are other things happening, like diamagnetic materials, but this is a very simplified version of what's happening here. The ions in the grape. Move in a way to produce an opposing magnetic field. All right, there you go. Oh, yeah, well, never mind. They say repulsion occurs here. That's good. Okay, that's the end of that assignment. Hopefully you did well. I'll see you in the next video. Bye.